Okay, hello everybody. In this video, I'm going to be talking about local linearity and how it can be used to approximate weird functions that we don't necessarily when we don't necessarily have a calculator. Like for example, like a natural log or something. Uh, we might know we might not know the exact value of natural log of um, 2.1 or something, or e to the power of 0.001 or something like that. But we can actually use this tool to help us out a little bit. And let's talk about why this works. So hopefully you're already familiar with tangent lines. They have to do with thinking about instantaneous rates of change and tangent slopes at a point. So hopefully this isn't a new concept to you, but like for example, let's imagine that we have a tangent line like right here. Let's say it's tangent at x equals 0. So that's kind of my approximation for what this tangent line might look like. It'll look something like this, right? And if you think about it, if you were to zoom in really far into the spot, and I'll show that when we get into Desmos later in the video, suspiciously, you actually act very similarly to what this weird function is doing. If you're only looking, if you're zooming into this one point where you're tangent to that line, it actually kind of serves as a good approximation. So the idea is that if we can find a tangent line to a function, um, like around here, and we can essentially use the tangent line to approximate values that would otherwise be difficult to do if we didn't necessarily have a calculator or something like that. So that's what I'm gonna do in this video. So first things first, what's find the tangent line, the equation for the tangent line to this function over here, um, at x equals 0. So before I get into that, first things first, let's actually find f prime for this function. So it looks like we have two functions multiplying. We have a product of two functions here. We have x. We think of that as a function. And it's a pretty easy function, but it's still a function. And then we're multiplying this by e to the x. So whenever you have two functions, a product of two functions, that's kind of an indicator that you'll use product rule. And this video isn't an introduction to product rule. Hopefully you've kind of already done product rule and stuff. So anyway, I'm going to do f prime of x. Okay, so the way I like to do product rule is I like to take the derivative of the first, and so this will just be 1 times e to the x, so I'll just write e to the x just to save some space because this will just be 1, and then I'm going to add x times the derivative of e to the x, which will just be e to the x, right? So we actually have a pretty easy looking um, answer for our derivative here, and just to make things extra clean, I'm going to factor out an e to the x, so it looks extra nice. Okay, so this is our derivative. This is what it looks like. And what's first before we even a critical component of our tangent line is the slope, right? So let's evaluate f prime at 0, because that's the area that we're interested in. And then we can use this line to approximate values around 0. So I'm just going to figure out what this is at 0. So this will be e to the 0 times 0 plus 1. So e to the 0 is just 1, right? So this will be 1 times 0 plus 0 is just 1. So it looks like we have a slope of 1. And you know what? That actually kind of looks about right. If we were to expand out um, where this line might go, it kind of looks like it does have a slope of 1. So it looks like we're on the right track here. It's always nice to think about is this too big? Is this too small? Does this look right in my head? Because sometimes you can make a mistake, and that's an easy way to fix yourself. Like if you were to get a slope of I don't know, 100, you'd be like, oh, I think I may have done something wrong because that doesn't look quite right. So it's always nice to look at Desmos just to double check your answer and see if it looks right. So it looks like we have our slope, and then using our slope, we can construct a tangent line. And I hope that you guys get used to doing this because it's something you're gonna have to do a lot in calculus. So you're gonna be finding the equations for a lot of tangent lines. So I'm just gonna name this line over here. I'm just gonna call it g of x. And I know that the slope is just going to be 1. And I know what real quickly, let's evaluate when we're constructing our line, it's going to be x plus 0 because we're evaluating it at 0, and then plus it would actually be x minus 0. In this case, it doesn't matter for us because it's 0, so it doesn't really matter, but let's just do this anyway. So I think this is point slope form, I'm pretty sure. Uh, I'm a little rusty on the names of these. I just kind of use them. So if we think about it, f of 0 is just 0, right? And then x minus 0 is just x, and then 1 times x. So really, we actually have a super simple function. It's literally just g of x is equal to x. And that makes sense because we have a slope of 1, and we're not moving it up or down or left and right or anything. It's just it starts at the origin. So so here is our equation for the line tangent to f of x at x equals 0. Okay, so we can actually use this we can actually use this line to approximate what f of 0.1 is. Now it's important to not go too far away from 0, because if you see, like if I were to extend out uh, this line, it becomes less and less and less accurate as we go on, right? Like we're completely off once we go here. F of x is increasing just so much faster than this constant slope that it just doesn't become a viable approximation anymore. So that's why we're only looking around 0 over here. So okay, um, so I can say that f of 0.1 is going to be that's going to be approximately the same as g of 0.1, just because of how they kind of behave the same around 0. So um, I actually made this really easy for myself by accident, but g of 0.1, that's just x, right? That's 0.1. So just looking at this graph, I can say that f.01 is just going to be it's going to be approximately equal to 0.1, which is pretty cool. We just kind of approximated a value for this graph that looks kind of scary because it has like e to the power of x, and I don't know about you guys, but I don't know e to the 0.1 off the top of my head. That gets pretty weird. So um, now let's actually look at Desmos and see what it looks like, just to make sure that we got our approximations right. All right, so I've got Desmos pulled up here. I've graphed our f of x function, which is x times e to the power of x, and it looks pretty cool, just like this, right? So right here, I kind of graphed our tangent line at x equals 0 to this graph, and then we use it as an approximation, right? And I kind of want to make a point about why this works, right? Because if we keep on zooming in, zooming in, zooming in, zooming in, zooming in, zooming in, we're getting super small now. These literally look like the same. Uh, these literally look like the same function now. They look linear, and that's a really cool thing about functions in general. Is that like even if I were to go well, right here or something. It still looks pretty curvy, right? But it's let's do it here. So like it looks pretty curvy, but the further I zoom in, it's starting to just look like a flat line, which is interesting, right? Because just basic calculus knowledge, we would kind of look at this and say, oh, okay, well we have a slope of 0 here just because it's a minimum over here. But it's really interesting, this idea that if we zoom in further and further, our function looks linear. It's a cool idea, and it's a fun idea of thinking of functions that certainly is used a lot in calculus. So that's why we can essentially use this idea that we can kind of approximate values of a weird function using a linear function, just because of this concept of local linearity. So um, over here, I have our points that we approximated this f of 0.1 to be, and we figured out it was 0.1, 0.1, because this slope is just y is equal to x, right? So I'm going to go ahead and put it on here, and as you can see, of course it's on our graph here, right? Because if it wasn't on our graph, we would have been doing something wrong. But if we actually zoom out, and I'm actually going to hide this graph so we can just look in the context of the graph we're trying to approximate. This looks like it's on that graph. Like you're not far off at all. Like of course, if you keep on zooming in, it looks like it's worse off and worse off and worse off. But if you really look deeply into it, it looks like we're only off, if we look at 0.1, 0.11, it looks like we're only off by like 100th or something. Which is pretty darn good considering we just kind of were lazy and we decided to do it this other way, which is a lot easier, right? So anyway, this is the idea of local linearity. This will probably come up at some point. I don't know if it's guaranteed to be on the AP test, but it's still really helpful to learn because it's just the idea that you can approximate difficult graphs like trigonometric graphs and natural logs like logarithmic graphs, and other things like that. You can just approximate them with tangent lines. It's such a cool idea. And a bit of a spoiler alert, this will actually come back if you keep on going into calculus. You'll go into Taylor's series, which is essentially just taking approximations with a tangent line to the next level, and it's super exciting when that happens. So that's what you have to look forward to. It's pretty cool because this is mainly like a sneak peek of using polynomials to approximate uh, I think they're called transcendental functions. They're functions that just behave kind of weirdly and difficult, and we need calculators to figure out what's going on there. So, anyway, I hope you found this video helpful. It's pretty cool that you can just use approximations to cheat your way through things and get a good idea of what's going on. So, anyway, thanks for watching, and I wish you luck on your future calculus endeavors.